Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let me start off by thanking the organizers. This is the first time I'm giving a talk, but my second time at this Mysore Park, because last time I was on the other side and I was an organizer. So I appreciate how much work goes into organizing an event like this. So thank you to the organizers, and thank you for inviting me. So today I will talk about a new class of methods that we are trying to develop for handling very, very large data sets and doing large-scale data analysis. Okay, and this is joint work with some of my students, Cho, Donghyuk, and Hsieh, and a faculty member, Pradeep Ravikumar. Okay. So, you hear all this talk about big data. Well, what's new? What is new is that instead of the situation 20 years ago where we were getting a lot of structured data, now there's a lot of unstructured data that is growing immensely. So you have network data, for example, at LinkedIn, in biology, and the kinds of things that you want to do is you want to try and predict maybe that's resonating. So you may want to try and predict people you may know. This is the problem of link prediction. You have fMRI data. They are looking at trying to establish relationships between different regions of the brain. You may look at the voxel data that comes up from fMRI and trying to get techniques that automatically try and estimate relationships between different parts. You have a lot of images, video, email data. And one of the things that you might want to do is identify, the objects within images, or you want to identify, for example, whether an email is spam or not spam. So that's the classical problem in machine learning of classification. And of course, the data is growing a lot. So it staggers you sometimes to hear about some of these numbers, like 250 million photographs uploaded per day on Facebook. So the data is clearly growing very fast. And the question is, we want to try and analyze it. So one approach is, we'll take our traditional machine learning algorithms, and we'll try and develop algorithms that use more and more hardware. Okay? You use parallel computing paradigms and do so. What I'm going to talk about is trying to also develop new kinds of algorithms that scale to these very, very large data sets. So divide and conquer is a very common and successful paradigm in computer science and in applied mathematics. So one of the organizers just walked in, so glad he could make it. This is sort of a cartoon of sorting n numbers using an algorithm called merge sort. Okay? There, the idea is that you take a very large problem, suppose you have many, many numbers, you divide the problem into subproblems, you keep on dividing the problem, and then you come to a small enough problem that you then will compute the solution. So in terms of merge sort, it'll be trying to sort this sublist of the total list of the numbers. And then once you've computed this subproblem, then you will somehow merge these solutions and get a solution to the bigger subproblem. And then you go up the tree and finally you get a solution for the whole problem. Okay? And this paradigm is very common in computer science. I've said sorting, for example. In applied mathematics, there is a problem called the n-body problem. You can do those calculations in sort of n log n time because of a divide and conquer strategy. When an impression this made on me was when I looked at, there's something called the symmetric eigenvalue problem, and people wanted to design new algorithms for parallelizing. And then they came up with a divide and conquer algorithm, and it was immensely successful. But what happened in that case was not only was the algorithm successful in parallel, but it actually ended up being the best algorithm in serial also. So that's what a lot of people use throughout the word big data. Some people are skeptical about it, whether it's just a hype. I truly believe that something quite good will come out of it, because I think it'll spur people on to look at new algorithms, and we will really benefit from the algorithms that come out. So the question is, can we use this kind of paradigm in machine learning problems?
I think the biggest criticism we probably see in this domain is that we all talk about big data. We all work on the big. We all talk about everything about big data, but where is the big data?
Oh, you mean where it comes from, or?
As in, like, where are the instances where such a big data is actually required?
I mean, I gave examples over here of, if you are at many companies, not just, these massive companies, but even medium-sized companies, you're going to generate data like this. Okay? Now, when you do the analysis, whether you sort of subsample or you work on the whole data, you might say, well, subsampling will do, but maybe you work on the entire data because there's going to be a very long tail. So in that sense, you may want to analyze the whole data in once. And that will vary from application to application. Yeah?
So I have a question of what do people consider big? Because what we consider big volume speech is very different than what vision people consider as well. So
This is big.
see, I would say like 1 million is not
1 billion users or one? I see. It depends also on, I mean, you can always sort of define big as something that you cannot do on a serial machine, right? So you need more. So for example, if someone gives me a data set with 40,000 variables, if I want to try and estimate a sparse inverse covariance matrix, I cannot do it on a single machine right now. So I will need more scalable solutions.
Just about the question of subsampling, I mean, there are many data sets where it is sparse. There are many kinds of data where it is hard to figure out how to subsample. If you have a ratings matrix, user item ratings matrix, it's hard to figure out what to subsample. The data is structured. So, but if you just had a classification problem, maybe you could think about some subsampling.
Right. And a lot of people will talk about pre-processing before doing data analysis, but wouldn't life be wonderful if you can just take your big CD or so and out pop the answers? Right? So there's a lot of value to avoiding a lot of human intervention in the loop. So here is sort of an example. Okay, so here you can think of as a representation of a network. And what you might want to do is you might want to try and identify these communities, let's say D1, D2, D3. You take your big data, you divide it into these parts. You may want to do this division either in a randomized manner, but you may want to be a little bit clever to try and identify these communities. But it has to be fast to be able to do your subsequent analysis. And then you can see that there are subcommunities within communities. You keep on dividing, then you get something over here, small enough problems that you can then not only do on a serial machine, do easily, but also there is going to be immense amount of parallelism to be exploited over here. And then once you get the solutions of these problems, then you combine them in some way to get a model. Okay? And maybe there is a possibility that this model actually might be better because you may be able to look at data at different scales. So what I'm going to do in this talk is give you 3 concrete examples where we've used divide and conquer methods. Okay? These are somewhat classical problems in machine learning. So the first problem is going to be doing nonlinear support vector machines, and I'll talk about a divide and conquer method. Then dimensionality reduction for very large networks, and then trying to apply it to the link prediction problem in social network analysis. And then this problem that was motivated by looking at fMRI data, trying to establish relationships between different voxels in that case. So I'm going to now go into kernel SVMs. There are many experts here in the audience, so I'm actually going to try and spend, I think, more time on this problem than on the other two. So this is the classical picture that you see in any textbook on support vector machines. It's a widely used classifier. Okay, the setting is that you're given training data. These are points which are d-dimensional. And let's just consider the special case where, simple case where there are two classes. Okay, so the red class or the green class, the red class is -1, the green class is +1. Okay. And the goal in support vector machines is to find a hyperplane that separates these two classes of data. And the margin is given by this, if W is the normal to this hyperplane, then the margin is given by 2 divided by the norm of W. And so what you want to try and do is maximize the margin while being able to separate the data using the hyperplane. Okay? And then, of course, you can allow violations if the data is not linearly separable by giving a linear penalty as you go away from the margin. So once you do that, the problem becomes you're trying to maximize the margin. Remember, the margin was 2 divided by the norm of W, the 2 norm. And so I can try and minimize the 2 norm of W subject to these constraints. And then if I allow violations, then I can have these slack variables, and these slack variables need to be non-negative, so the whole problem can be formulated as a quadratic program. Okay? So, and this parameter C trades off sort of this regularization versus the summation of the psi i's, which can be looked upon as hinge laws. Okay? So this is what's called the linear support vector machine. And then again, what happens if the data is not linearly separable? Then what you can do, for example, in this case, is to map the data to, if it's 2-dimensional data, you map it to a higher dimensional data by combining features non-linearly. And the goal is such that the data will become linearly separable in the higher dimensional space. Okay? But you still don't want to compute in this very high dimensional space, so there's something called the kernel trick, where you can just look at the inner products or the gram matrix between the data in this high dimensional space. Okay? And then you can look at the dual problem for the SVM, support vector machine. So this is what we will be concentrating on. So it becomes this quadratic objective subject to these bound constraints. The alphas are called the dual variables, and that's what we need to try and find out. There are going to be the number of alphas is going to be the number of training points. So if you give me a data with 1 million training points, there are going to be 1 million values of alpha that we need to know. And then at the optimal, you can express this normal to the hyperplane as a linear combination of a subset or of the training data. So some of them might be alphas, many of them might be zeros, in which case the W will be expressible only over a small set of these training data. And note that you don't actually, you don't need to compute W explicitly, because what is finally needed is classification. And the classification can be done by taking this inner product with the training point. So then we can express this, the classification or the prediction by just using these kernel functions. Okay, or the kernel values. So you don't never need to compute explicitly these high dimensional feature vectors as long as you have this kernel function. So what kind of kernels do people use? The Gaussian kernel is probably the most widely used. You of course have the linear SVM or the linear kernel, then you can have polynomial kernels. Now let's think about what happens to big data. So if I have lots and lots of training data, will I be able to run a nonlinear SVM that solves this quadratic program efficiently with enough memory? So what is the memory requirement? Well, the memory requirement is going to be order n square if you pre-compute the kernel matrix. That you can get around by computing the kernel matrix on demand. What about the time? Generally, it's going to take cubic in the number of samples, and that might be too expensive. So for example, if we take a data set, this is a handwriting digits data sets, MNIST data set, 8 million samples. If you run one of the state-of-the-art methods for solving the nonlinear SVM, then it takes more than 3 days to train on this data set. Okay, and that's a lot. So actually Manik was sitting with me for dinner, and he actually gave me a nice motivating story. So he apparently in his class decided to give to these IIT Delhi students problems in Kaggle. Kaggle is a website where you can have upload data sets, I guess, and you can submit methods, and you can see which method does well on which data set. So he submitted a data, the cover type data that I'm going to talk about, where the linear SVM does very poorly, the nonlinear SVM does much better. It's a data set with about 500,000 samples. And he said none of the students had enough patience to run the nonlinear SVM because they tried for 6 hours, the method did not finish, so they tried other methods. Okay? So what my talk is that in the next instance of this course, that Manik can actually have these students work on this data set, and it will not take 6 hours. It will take much smaller. And how do we get there? It will be by using this divide and conquer strategy. So far what I have said is classical. Now let's get into the sort of the new algorithm that we have developed. So here is a motivation. Okay? So we'll have all these data points. We're going to try and divide them into different sets or clusters. So it's equivalent to partitioning the alpha into these k subsets, V1 through Vk. And then what we will do is we will solve each of these problems independently. And then we can just think about gluing the solutions together. We'll get a feasible solution, obviously, because all these values are less than or equal to C. And the hope is that this will be a good approximate solution. Okay? Now we'll get to why this might be a good approximate solution and in which case it will be a good approximate solution. Well, if you just carry out this thought process, then, well, you can see that if each partition is of size n by k, suppose all the partitions are equal in size, then you'll reduce the computation to compute this value, this vector alpha bar, from n squared to n squared divided by k squared. Then I'll be solving k of these problems. Each problem is of size n by k. If the computation is cubic, then again I'll be able to reduce by a factor of k squared the computation that's involved. So that's the first thought process that comes to your mind if you're thinking of a divide and conquer method.
So the main approximation here is that the cross terms are...
Yeah, you're being too quick. I have a whole talk to go through. All right? So it'll, I teach at the university, so I'll get to all these things. So do you want to ask me a question or you want to hold it off? You can ask me, go ahead. I don't want to discourage you. We will solve the support vector machine exactly. We will solve that quadratic program exactly. So there is going to be no approximation. You're moving too fast. So let me go through my next few slides, okay, and then you ask me these questions. Okay? So this is just producing this alpha bar, and then what we want to do is we want to solve for the SVM. So if you want to do that, you can take a software like libSVM. You can feed in the alpha bar as an initial point, and then you can start libSVM. So then you will get the global optimal for this quadratic program. So you will get the nonlinear support vector machine. The question is, has it bought you anything? Is it any use? Okay? So when would it be of use? If the alpha bar was close to the alpha star, which denotes the optimal, the global optimal of the QP, right? Then it will be good. By chance, suppose alpha bar was equal to alpha star, we'll be ecstatic. But that's not going to happen. And then at every step, you're going to the alphas that are non-zero will be the support vector machine, support vectors. So if for some way we actually get good support vectors identification over here, that means the alpha bars that are non-zero over here, or the alpha bars that are zero over here, also turn out to be zeros over there, then it will be very good. So alpha bar will be a good solution in this case. And let's say the block coordinate descent method or block coordinate ascent method of libSVM will actually converge very quickly. Now the question is, when can this happen? So rather than partitioning the problem randomly, it turns out that if we do some sort of clustering to get to a partition, then it performs very well. So let's now go through the process of showing that. Suppose I have this alpha bar as the solution of the kernel SVM. Then I can think about using an approximate kernel. Okay? This just says that I'm going to ignore the off-diagonal blocks. So I can look at the corresponding kernel matrix, and instead of having G, which is the actual kernel matrix, I have G tilde, where I have zeroed out the off-diagonal blocks. Okay? So then you can say, where is the error coming from? So I can quantify this by a quantity called d pi, which is the sum of the off-diagonal elements over here. Okay? And then what I will show is, in the next few slides, that if I can drive d pi down, then my alpha bar will be close to alpha star. Okay? So that's the first theorem. If I start with alpha bar, this f refers to the quadratic objective function value. Right? So this is, half of alpha transpose q alpha minus e transpose alpha. So clearly f alpha star is less than equal to f alpha bar, because alpha star is the global optimal. And then what you can show is that the difference between these values is bounded by half c squared, where c is this trade-off parameter, times d pi, which is the sum of the off-diagonal blocks. And furthermore, because this is a quadratic, then there's sort of an inverse problem. Given that the alphas are close, how close are the alpha bars? And they'll be close modulo the smallest singular value or the eigenvalue of the kernel matrix. Right? So what we want is a partition which minimizes d pi. What is the best partition that minimizes d pi? Well, just take one partition. Then there's going to be no off-diagonal element, and clearly alpha bar will be identical to alpha star. But that's not helping me, right? Because I want to try and reduce the computation. So I have two goals. One is I want to try and minimize d pi, and the other is I want to try and have balanced cluster sizes for efficient training. So what I will then do is I can try and use kernel k-means, because you're giving me the kernel, I'll use that as a basis for trying to partition the data. And then, of course, you might say, well, kernel k-means itself is going to cost quite a lot, but remember, this is going to be a means towards an end. I'm not trying to get clustering. I'm not going to try and output the clustering. So typically what we will do is we'll take a subset of the samples of size m, which is much, much smaller than the number of points. We'll do the clustering, and then run the clustering algorithm, and then we'll just fold all the data into these clusters. So just to give you an idea about how effective this strategy can be, here is the plot. Here is this cover type data set that Manik gave to his students. I've taken a subset 10,000 samples, because to compute this bound is not trivial, okay? Because it involves some work to compute this bound. So on the x-axis, on the left plot over here, I've given the value, the absolute value of the difference in the objectives. So this is plotting f alpha bar minus f alpha star. This is on an absolute scale. This is on a logarithmic scale. So here you see that if you look at the bound, it's very small. If you run the algorithm using kernel k-means, it's indistinguishable in the absolute value setting. But if you use a random partition, it's much worse. So if I just decided that I'm going to partition the data randomly, and then compute alpha bar and see how alpha bar differs from alpha star, then this difference is huge. And this is amplified over here. So when this is on a logarithmic scale, and by the way, this is 8 clusters, 16 clusters, 32, 64, 128 clusters. So you can see that the bound is actually reasonably close to what happens, the actual value that we observe. So by doing this strategy, we're able to get alpha bars that are reasonably good approximations to alpha star. And then we can actually also prove a theorem that says that the support vectors also get identified fairly quickly in this process. You can't always do it, but if one of my alpha bars is 0, and if I look at the gradient and the component of that gradient is big enough, then you can show that when you try and compute alpha star, that's going to remain anchored at 0. Okay? The slight issue is that these bounds are not necessarily computable. We haven't addressed that problem too much, but we can try and approximate these values. So this is an example of the support vectors. So suppose we have this scheme now where I'm going to partition the data, going to keep on partitioning the data, and then I'm going to compute alpha bars at the bottom, and then compute the alphas for the parents, and keep on going up the tree. So up the tree, when I look at the whole problem, I'm solving the actual kernel SVM problem. There's no approximation going on. Okay? So here is, as you go up the tree, even with 256 partitions at the leaf level, 85% of the support vectors are correctly identified. Okay? So as you go, for example, with 4 clusters, then almost 100% of the support vectors are identified. And that's why the method ends up being faster. And this is in comparison to another method, which is Cascade SVM, which does partition the data, but randomly. And then it has a different strategy, so it actually does not compute the actual support vector solution. So what we want to do is, we have a trade-off. We have this parameter k, which is the number of partitions. If I choose a small k, then I'm going to have a smaller approximation error, but it will take more time to solve the subproblems. If I have a larger value of k, then I'll have a worse solution. It's going to be quick. So there's a trade-off. So what we do is, instead of just doing one partition, we do a hierarchical partitioning. So what we will do is, we'll do a clustering over here, then we'll look at this cluster and subcluster over here. We'll do this data division, and then we will solve the leaf problems. The alpha bars from the leaf problems, we'll be able to solve for the alpha bar, for the alpha values for the parent, and then go up the tree. And finally, we'll solve the original problem. So how well does this compare with other methods? So we'll get to that. The interesting thing is, we can actually try and do early prediction. So what do I mean by early prediction? Maybe stop over here. So that's one thought process is, you have these alpha bars over here, alpha bars here, alpha bars here, alpha bars here. I can go ahead and solve the whole problem, but I could think about using those alpha bars themselves. So that's what we will call early termination. So that's not computing the exact SVM solution, but let's see, it's obviously going to be a little bit faster, quite a bit faster it turns out. And then let's see what the accuracies are going to be in the end task of classification. So remember, the goal is not really to solve this quadratic program exactly. The goal is to get a good solution to the classification problem. Okay, so how would you then do the prediction? You have, if you do early prediction or early termination, you will have faster training time. The prediction accuracy is going to be, it turns out, is actually close to or sometimes even better than the global SVM solution. How will you do the prediction? It turns out that the best thing to do is to use the block diagonal kernel. You can use the overall kernel. It turns out that this gives worse accuracies than over here. The nice thing is that if I do my early termination, my potential number of support vectors is going to be reduced by a factor of k. As a result, the test time will also be faster than having to use all the support, potentially more support vectors. Okay? So it turns out that this is very useful in practice. So we have sort of extensive comparisons. So this paper is on arXiv, and it just got accepted to ICML in Beijing. So you can actually look at the results in arXiv if you wanted to. So I'll call our method the divide and conquer support vector machine method, SVM, DC-SVM, and then I will denote by early termination DC-SVM early. So DC-SVM, the solution is going to be exactly the same as the lib-SVM solution, modulo some epsilon. Right? And then there are a bunch of other methods. So let's look at the results. So this is Web 3 datasets, 280,000, about 500,000, 8 million. This is the MNIST dataset, right? So if you look at over here, you know, the DC-SVM, the divide and conquer SVM takes 71,000 seconds, as opposed to 300,000 seconds. So it's faster by a factor of what, 4.5. And the accuracy is very much comparable to libSVM. These are numbers on a sequential machine. We actually have not programmed it on a parallel machine. Right? So one could get further speed ups because there is more opportunity for parallelism over here. But these are sequential numbers. And the time, but then look at DC-SVM early. So if I do early termination, you look at the accuracies, very close to the SVM, very close to the overall SVM solution, very close to the overall SVM solution. And the amount of time is 1/7 of this time. Okay? So it's about 30 times faster than the libSVM solution. So if it took 3 days, but for libSVM, how much time will it take? 1/30 of 3 days. So just over an hour, right? So you can, instead of having to sleep overnight 3 days and come back and get the results, you can go have lunch and you can get the results when you come back. Okay. Then in terms of what you can also do is you can look at the objective function value as you go up the tree. So this is DC-SVM, and you can see that this is different levels of the tree. So this is the finally globally optimal solution, and it takes much time, it converges much faster than having to do libSVM because you end up getting a much, much better starting point. And that's when you start working on the overall problem. You work on these smaller problems, you do optimization there, you end up getting better solutions for the whole problem. As a result, the global, that block coordinate solve that one has to do on the whole problem, the time is, it converges much faster. Okay. And then over here is actually quite interesting over here. Look at this plot. So as this is MNIST data, as you increase sort of the number of levels, the objective function value decreases only at the last step. But if you look at the prediction accuracy, it goes from being maybe not so good at the leaf to quite good as you get closer to the root. And this is a phenomenon that we've observed over and over again. And this, I feel, is actually a very interesting table. Right? So this, for example, if you use a Gaussian kernel SVM, you have two parameters. You have the gamma, which is the width of the kernel, and you have this parameter C, which is the trade-off. Right? So the question is, for different values of C and gamma, how do the methods behave? Okay? So that's what we've shown here for one data set. In the paper, many different data sets are shown. So we vary C in a grid, we vary gamma in a grid, and we have now tabulated results for DC-SVM early, the divide and conquer SVM, and compared it to libSVM. Because this computes exactly the same solution as libSVM, the accuracy numbers are pretty much identical. Okay? The time is faster than libSVM. The time here for DC-SVM, the bold are the best numbers. Okay? It's always faster. But look at the accuracy numbers. So here, the best performance here is about 99%. Okay? DC-SVM is also pretty close. What's the worst performance over here? Oh, it goes to 61% when C and gamma are not good. So you might say, well, you try different C's and gammas. What happens over here? Well, the performance is actually not that bad. So that's an intriguing part of this, because what's happening is that we are building these different models at different scales of the data. And in some sense, we might be smoothing out some noise which is present in the data set or in the model. Okay? So this is actually an interesting, so you might ask you the question like, why ever use DC-SVM? Why not always use DC-SVM early? And that's a candidate. I mean, it's a plausible thing to do, except that I cannot give you a guarantee that DC-SVM early computes the maximum margin hyperplane. Yeah?
Actually, my question was, how is it that DC-SVM is actually doing better than libSVM? It's 93.7 and 92.6, I think.
Where is it? It's probably within noise factor. I mean, there is an epsilon, right? There's a termination criterion, and we may have used a slightly different termination criterion in the different methods.
So you had also mentioned in a previous slide that actually the early
some cases. So for example here, 86% here and 61%. That's a big difference. So that's not for the best values of C and gamma, but it is the difference is big in terms of the accuracy.
But why does that happen? Why does it get a solution better?
So I don't have a bulletproof answer. Like I can't prove a theorem for you. But what my feeling is that there may be some these values of C and gamma are obviously not good. That's actually correct. Oh, so but I don't know if over here he may have turned off the bias term also. I'm not sure. But it's your student who, it's actually his master student who's now my PhD student. So I don't know what he did because he modified the lib-SVM code to turn it into DC-SVM. So I'll have to check with him. He's leaving for Taiwan soon, so you might be able to check with him quicker than me.
So, can you give more indication into the kind of aggregation you think is happening? Like, if you compare the last process, right?
Yeah, I haven't thought too much about it, but maybe we can think on the fly, right? So gamma is small over here, so it looks like it's happening for a small value of gamma, right? When gamma is very small, then it tends.
It becomes more diagonally dominant.
So,
Yeah.
gamma is in the numerator,
Gamma is in the numerator, e to the power minus gamma.
So it becomes more like.
So it becomes more diagonally dominant.
Right. I see.
And if gamma is small, then you just get it. Essentially, for gamma equals 0, you get an identity.
Yes.
It's other way around, gamma is in the numerator.
On the first row where you have the 86 and 61, do you have the corresponding accuracy numbers in the test set?
Oh, these are accuracy numbers on the test set. Yeah. I mean, that's standard machine learning that we train on the training set and then we are doing testing on the test set. And I don't know, this might be, he might have, I forget whether this is done with not cross-validation, but on, different splits of the training and test data. Yeah, question?
Are there some numbers on the
Memory
memory
use. So the memory use was, if you wanted to store the entire kernel matrix, compute the kernel matrix and use it. What lib-SVM does and what we do is essentially compute it on demand, right? So memory is not that much of an issue. Although, for example, when we have a small problem, we can actually do the computation once and for all and then reuse it. Again, I don't know the specifics of the code. By the way, there is actually a web page for this paper and the code's also available. So you guys are actually welcome to try out the code. This is, because we don't compute the entire kernel matrix and try to store it. The data set is in memory, I forget now the dimensionality in these cases. I don't think the dimensionality is that big that you cannot hold the data set in memory. What's that?
They are not large. So for
Yeah.
any space, 784.
Yeah, so the data is not.
The current time is like 50.
But that's what would happen, right? So for example, if you cannot hold the data in memory, then you have no option but then to try and distributed memory solution. But what I'm saying is that this actually will give you a better algorithm which will perform better on distributed memory. Was there another question there? Yeah, you had a question. Right now I'm just talking about this SVM problem. So whatever we've shown is for the SVM problem, which is even more, which is not just convex, but it's a specific bound constrained quadratic optimization problem. I can foresee where you're going, where you can try doing this on some different objective function, right? And there, I'll come to that because the sparse inverse covariance selection problem has a very, very different objective function. Again, that's convex. And over there, we end up also using a divide and conquer algorithm, except the division strategy is also then tailored to that problem. So if you see over here, the division was using the actual kernel. So it was really tied to the support vector machine, the kernel SVM problem. So that's what I will conclude by, that suppose you want to try and generalize this class of methods to different problems, then there should be something that you can do. We don't drop anything. That gradient condition is not easy to check. So this condition, we actually never compute d pi, because that would mean that you have to compute the entire kernel matrix. I guess we could compute it for small problems, right? We could compute it towards the bottom of the tree, and then we could check it, and then we could discard some values. That's actually a good point. Yeah. He's had his hand raised for a while.
What is the value of k used here?
So from this plot, it's 4 and then 16, 64, 256. So 4 partitions in each case. I don't remember. This one? I don't remember. I think we used 3 levels, and I think it's k equal to 4. But we can go back to the paper and look at that.
So basically, 3 has a fan out of 4 and then
4. Yeah, and these are all questions, in some sense. Why 4 at every stage? Can you try and do model selection where you figure out the number of clusters? There are all these parameters that could be tuned in the code. Yeah, Vishay?
So I just have one comment and just one question. So I was wondering if you can actually do this similar to shrinking. Can you get only the support vectors at the lower level, only take them to the higher level, solve the subproblem on only the support vectors?
That's what I believe this cascade SVM tries to do, without doing this SVM partitioning at the top, without doing the kernel clustering at the top. So it does random partitioning. Chunking or so. Chunk is, right? Yeah.
But they don't get it. They don't solve exactly solve the original.
Exactly.
Yeah.
But then what tested is that they try to fill again.
Yeah.
But then they do like random selection.
Random selection, and I believe they don't actually also solve the global SVM. Here, you run the DC-SVM, you get the actual SVM solution. But you have the option, and you can start the program, and you can actually terminate early. You'll actually get some results early on in the process.
So in cascade, basically, they have to, I think they do solve the global thing, but the problem is that the issue is that they have to iterate again and again through this process.
Yeah, I don't think they solve the whole thing. We can look at the paper again, but.
Yeah, they do.
Okay.
Actually,
We can look at that. Yeah.
That was where I was going to next.
Yeah. So we do, I will say that we actually do refine the clustering. So I didn't talk about a little section, but we do refine the clustering as you go up the tree. And we use the support vectors over there. So it turns out that for the support vector, you can actually figure out the support vectors and then confine the clustering to some of the support vectors.
So what I was getting to next is basically this, that sort of, do you have a sense of what part of your gains are coming because you're doing this initial clustering versus what part of the gains are coming because of putting the solutions together? So what I mean is, say conceptually, if we took something like a cascade SVM and did the kmeans first and did the division of the data, then would cascade SVM perform much better?
You mean because they only are propagating the support vectors or so? Yeah, that's something we have not checked. I mean, for us, it's going hand in hand. Now you're sort of saying is, how can we maybe even make this algorithm more efficient? Yeah.
I think optimal gamma will give you much good information on that.
Was there another question? A couple of questions there? Yeah. Yeah. So we basically have alpha bar, the optimal solutions for the subproblems. We then use that. We merge, basically take the use the optimal solution for both of them, and use that as an initial point for libSVM like solver. So it will basically do coordinate ascent but starting from that initial point. So we are solving the optimization problem. Was there a question there, or? Okay, yeah. Yeah.
So there are other techniques to get approximations. For example, there is this whole line of model of random features, which will, again, in a guaranteed manner, give you.
So we have fast food over here.
Yeah, so,
They just give very. I mean, if you look at the quality of the solutions, I mean, I know that they have, there is theory and so on. The approximation actually is quite poor. So, when you try and plot things like, where was my plot? So this plot is very convincing, right? So, I mean, you may argue that this bound might be bad. The one nice thing is that you have to realize that this is an exponentially declining kernel. This is a Gaussian kernel, right? And so it turns out that the bound is actually pretty good. And you can look at the F alpha values, right? I mean, this is 10 to the power minus 10 difference between alpha bar and alpha star. That's pretty good. Their constants are much bigger. Yeah?
Algorithms which can cluster data without having to specify the number of components, like if you want to get a adaptive tree structure.
Yeah, but we want something fast.
Yeah, so there's simple variations of clustering algorithms means that
Sure. Yeah, we can do that. I mean, lots of, so we're getting ideas for future papers, right? But I'm not going to do everything. So.
But do you think it's possible to find a number, a value of k automatically? So you have
The K, you mean so doing some sort of model selection and finding K, or? Yeah, you can try it. I mean, I just think that I worked a lot on clustering myself. I just think that's a tough problem. You can have a lot of theory behind it, but the results that you get in practice are not always very good.
So I think we take the question offline because I think there's much more to cover also.
Yeah, I mean, I did not want to enter because it's supposed to be interactive, and the fact that you have so many questions is good.
So catching the top of the break. So
10 minutes, okay. Okay, that's fine. So there are more results. Okay, so this actually shows that in some sense, by doing this early termination, we get actually something which is more robust, okay, than just the global SVM solution. Right? So I have 10 minutes, okay, and I kind of anticipated this. That's why I put the more recent work. I mean, I gave a version of this talk in Microsoft Research in May, and at that time we had not done that much work on the SVM problem. Okay, so today I concentrated mainly on the SVM problem. Now what I want to just convey to you is, well, there was this divide and conquer approach for this particular kernel SVM problems. I will tell you that divide and conquer basically works in two other settings, okay, two other concrete settings. One is social network analysis, so I'll go over this pretty quickly. This is, nodes represent individual people, edges represent relationships or friendships. This is the classic karate club network that's studied by sociologists. What do you want to do in network analysis? Well, you want to try and get proximity measures. Like if you take two people in this audience, they may not be friends, for example, on Facebook, but they may be linked with other people who are friends. They may be a path of length 2 in the network. Okay, in that sense, they are closer than if I take a random person off the street in Mysore. Right? So you want to try and get proximity measures, and the applications are you might want to try and do link prediction, which is given snapshots of the network. So this is a cartoon where you have 5 people in the network. Alice and Eve first become friends, then Bob and Dave, then Alice and Bob. And the question is, if you know the state of the network till this point, what can you predict might be the state of the network in the next time instant? So one way to do it is look at what's called friends of friends. That means if there are 2 people, they have a lot of friends in common, then they are more likely to become friends with each other. And that corresponds to a path of length 2 in the network. And then you can say, well, what about paths of length 3? What's the paths of length 4? And it turns out that there was a psychologist called Katz who looked at this and proposed this measure called the Katz measure. Okay? The Katz measure essentially computes what's called the resolvent of a matrix. So if I have an adjacency matrix, the Katz measure computes the inverse of I minus beta A. Beta is a particular number which is small enough. If it is small enough, then this is true. Okay? That you look at paths of length 2, you look at paths of length 3, you exponentially damp them by this factor beta, and then you can try and do friendship prediction. You look at f of a, this matrix valued function, you look at the large values in this matrix valued function, and those are the people who are more likely to become friends. But if my matrix is very large, let's say million, then there is no way that I can actually compute this. So then the question is, what can you do? You can try and do spectral approximations of the adjacency matrix, and that works because once you compute, let's say, the eigenvectors, then this function, let's say over here the power or here the inverse, just needs to be applied to an inner, much smaller matrix. Even this becomes quite expensive if the dimensionality is very big. So what we did was, we said, well, there is a community structure in the network, right? And within each community, there's subcommunities. So what we are going to do is, we are again going to find communities. So this is the analog of the kernel kmeans we were doing in the kernel SVM problem. We'll find subcommunities within communities, and then we'll get a similar tree-like structure. Then we will compute some approximations at the bottom, and similar to the SVM problem, we'll use that as initialization to finding the matrix approximation at the top level, at the parent level, and keep on going. As a result, let me just show this. Then you have, so this might be the spectral approximation at the top level, but then you get matrix approximations at the second level and the third level. Okay? Each of this actually gives you a prediction. So what we end up doing in this case is not just using this prediction, but we can actually combine all these predictions. That's like looking at data in the multiple scales. We've tried using this in the kernel SVM, we haven't seen that much advantage. There we just use the whatever top level we get. Okay? But here we saw an advantage in doing this. So just in summary, so this is an example. We've done sort of multi-scale link prediction using the CATS measure. Here are just some results. So this is a Flickr data set with about 2 million users, 40 million links, so pretty big. Again, just running on one machine. And by using this multi-scale predictor, we are actually able to almost double the precision. So for example, here is top K, so 100, so it's 13.7 or so, 13.3. About 13 out of 100 predictions are correct. They do become friends in the future. And if you compare to the, without this combining these divide and conquer method and combining these predictors, it's 7. So we're actually able to get a much, again, a better predictor by combining these predictors at different scales. So this is an even more complicated problem, but I have even less time to talk about it. So I have about 5 minutes. Right? So I'll try and go through this quickly. So this is an example where now you have a very different objective function than in the SVM problem. So finding the so you've probably heard about graphical models. So if my data comes from the multivariate Gaussian distribution, so I see samples y1 through yn from a normal distribution with mean mu and covariance matrix sigma. The goal is to try and, you only see the observations, but what you need to estimate is either the covariance matrix or the inverse covariance matrix. And what you can show is that the inverse covariance matrix captures the graph structure. So it's easy to show that if, for example, there is no link between, there is no edge in theta inverse. If you view theta as a graph, then if there is no edge between node I and node j, then these two variables are conditionally independent given the other variables. So given limited number of samples, but in very high dimensions, so for example, in fMRI data, you can actually have about 300,000 voxels, and the number of fMRIs might not be that many. Okay, so the number of samples is not that. So what people have proposed is to use an estimator which has this form. This is the maximum likelihood estimator regularized by this L1 regularizer. So this is a case where you have a convex objective which has a smooth part and a non-smooth part. The smooth part looks very intimidating. It's log determinant of some matrix with a linear term. And then this part is non-differentiable. So what we did, I've been working on this problem for about 3 years. What we did was developed a quadratic approximation method that does a Newton type of algorithm on this objective function. And then we were wanting to scale it to bigger data sets. So the question is, how do you scale it to bigger data sets? And then we said, well, how about trying to use divide and conquer methodology over it? And there was a slight precedent because there were these statisticians from Stanford who had made the following observation. So I'm going pretty quickly over here. Okay, so this matrix S is the sample covariance matrix. Okay, so that's easily computable, right? But in high dimensions, when you don't have that many samples, the sample covariance matrix will be singular. So you can't just invert it and get a good estimate for theta. That's why you use this kind of objective function. And what people have shown is that this estimator has good statistical properties. So I'm not talking about the statistical properties in this talk, but I'm just talking about solving for a positive definite matrix X such that this is minimized. What the Stanford statisticians observed is that I can look at what's called this thresholded covariance matrix. Remember, lambda is a regularization parameter. Sorry. The larger lambda is, the sparser my answer. Right? So if I make lambda larger and larger, it will be sparser. So what they observed is that you can take the thresholded covariance matrix. So lambda is a positive number. You take the thresholded covariance matrix. So the larger lambda is, the more zeros there are going to be over here. So what they said is that if the thresholded covariance matrix has multiple connected components, that means the problems are independent of each other, and the final answer you can get by solving these independent subproblems. Okay? So it's a very simple algorithm. You basically take your thresholded covariance matrix, think of it as a graph, find the number of connected components, solve the problem independently on each connected component. If lambda is large enough, this can lead to a substantial reduction in time. But in practice, what happens is that this sample covariance matrix and even the answer is block diagonal, and then there will be occasionally some relationships over here. And I was actually collaborating with somebody who was working on climate modeling, and what he was saying is that in that application, the faraway connections are the more interesting connections. So the one connections over here would be the more interesting connections. And if that's the case, so even if there are one element each in each of the off-diagonal elements over here, off-diagonal blocks, then this will just have one connected component and there will be no savings. Okay? So that's manifest over here. So if you take this G-Lasso code coming from the Stanford statisticians, you decrease lambda. It's quite fast when there are quite a few connected components, but as you decrease lambda, you get only one connected component, and then the algorithm has to work on the whole problem. So what we did was we realized that, well, you can actually do a divide and conquer approach over here. Okay? Again, we do a clustering of the nodes, solve the problem, the subproblems. We use the subproblem solutions to again seed the solution for the parent, and we go up the tree. And as a result, this algorithm is called DC-QUIC. Okay? QUIC was quadratic approximation of inverse covariance matrices. That was the method that we developed in this NIPS paper 2 years ago. Then you can see that this divide and conquer method is faster. And it doesn't suffer even when the connected components in the thresholded covariance matrix becomes just one, the algorithm degrades gracefully. It does not have this big spike. How do we do the clustering? Again, the clustering is in some sense customized. Okay? We look at the objective function, and we then sort of give a reason what kind of clustering we must have. Okay? And then we do a clustering. In this case, it was a thresholded covariance matrix, and then we ended up using some sort of graph partitioning software. So here is the sort of answers that we get. So suppose this is the final answer, right? This is what we want to get to. One option is I solve this problem in, the whole problem right from the beginning. What we end up doing is we partition the problem into subproblems. We will solve this, this independently of each other. Then we will combine the solutions, and you can see that we've gotten some more non-zeros over here. And then when we combine these two, we'll get this. And if we have a good clustering, okay, ideally you want a clustering of theta star. We don't have that. Okay, so we use the thresholded covariance matrix as a proxy. Okay, but you will see that in the end you actually get much sparser values. Okay, or the number of edges is much less in these off-diagonal blocks than over here. Okay, so I think I'm running out of time. I'll just sort of, this method is faster than other methods. Okay? So this is the convergence plot, this is a leukemia data set, a climate data set, and this is the divide and conquer method. And in fact, what we've done more recently is, so this paper appeared in a year ago at NIPS, and just in the NIPS that was held, a week or so ago, we have a method called BigData, which actually builds on this divide and conquer approach and can scale up to 1 million variables, okay, provided that the answer is sparse. So, in conclusion, what I've tried to do is present 3 concrete cases where this divide and conquer algorithm helps. That should naturally arouse curiosity. What other problems in large-scale data analysis can benefit from a divide and conquer approach? And there are probably many such applications. Regression. If I want to do matrix factorization, which is what Vishy will talk about, right, for collaborative filtering or recommendation. Multi-label learning, that's an interesting problem in industry. Then what are the corresponding algorithms? We have to do the division, but in each case, I tailored the division according to the problem I was looking at. Do we need to do it on a case-by-case basis? Or can we develop some sort of generalized kind of method to do the division and do the conquering? The third part is actually also very interesting, right? In the case of social network analysis, we got a combination of local and global models. And there we were able to combine them, and the result was quite good. What about other methods? Because we are getting these local, for example, in kernel SVM, we are getting these local classifiers also, these local kernel support vector machines. Can we combine them so as we get better accuracies? Can we build some sort of statistical theory that says whether those kinds of methods will be more robust? And I know that this is a workshop in distributed computation. So, this is an algorithm that's really ideally suited for distributed computation. So if you want to do parallelization, well, we need, by doing this division, we will probably need some dynamic load balancing because the work will be different. Okay? So in order to not be able to be stuck in this sort of bulk synchronous model, can we do some asynchronous parallelism? Okay? And that sort of segues nicely into Vishy's next talk, where he will talk about a method to do asynchronous parallelism on very big problems. So that's all that I have to say. Each of these has, there's a paper associated with each of these 3 methods that I talked about, and that's all. Thank you. Yeah, question? You mean accuracy or? Yeah.
And time taken is much less.
Yeah.
So, what are some reasons that I should not be using divide and conquer?
If you have time on your hand. If you would rather wait for 3 days for a result, then yes, you should stick with libSVM. Right? I mean, you're getting the same solution, but faster, right? Usually faster is better. Mm-hmm.
You're creating a whole bunch of smaller problems.
Exactly.
The size is the amount of time it takes to solve each problem.
Yeah.
Roughly the same, or they could be significantly.
So So that, I think there could be variations. Right? So that's why I think that when one does a parallel implementation of this, it's not going to be straightforward, but there is going to be some sort of dynamic load balancing to be done. And if you really notice, if I go back to, a lot of time is still spent in the top level. So if I was not to do early termination, so where is it? If you look at this, there's a lot of time spent in the top level. Okay? So you can't just say that I've divided the problem and there's no time that's really needed in merging the solutions. So over there, one would have to use techniques like the one we've developed with Vishy, that Vishy is going to talk about. So there are really both kinds of parallelism. One is sort of independent jobs, and then at the same time you're working on the same job, and you still need to develop some good methods to parallelize that part.
The number of subjobs here are like 4 cubed or something?
Again, it will depend on your particular problem, right? I mean, some cases maybe 4 cube might be good. In other cases, you may need to go deeper into the hierarchy.